The question is, if a current of 0.5 ampere flows through a metallic wire for 2 hours, 2 into 60 into 60 seconds, because we have to convert it into seconds. Then how many electrons would flow through the wire? So for how many electrons, we need to understand the relationship between the charge and electrons. We know that 1 Faraday, 96500 coulombs, corresponds to 1 mole of electrons. This is actually the charge of 1 mole of electrons. So if we can calculate charge from here, we can apply the unitary method. So the charge from here will be Q equals to IT, that is 0.5 into 7200, 3600 coulombs. Now we will apply this rule. If 96,500 coulombs correspond to 6.022 into 10 to the power 23 electrons, number of electrons asked, hence 3600 coulombs will correspond to 6.022 into 10 power 23 divided by 96,500 into 3600, and you will get the answer. Yes, approximately correct. Ashi, 2.25 into 10 power 22, number of electrons will be transferred in such cases. Yes, correct. If you take 96,500, then approximate value, but 96487, accurate value, but your answer will be considered correct, even if you consider 96500. If you consider 96500, it will be 2.24 into 10 to the power 22, which is correct. Next, suggest a list of metals that are extracted electrolytically. These are those metals which are at the bottom of the reactivity series. When I say at the bottom of the reactivity series, means they have very high reducing power. Means they can replace other metals. So lithium, sodium, potassium, if you remember, these were towards the bottom of the series. So sodium, potassium, calcium, lithium, magnesium, aluminum are extracted electrolytically. Yes, Vanna. Yes, Ashi, correct answer. So you need to just remember the answer. This question is asked as it is, has appeared many a times in board examination. Consider the reaction. What is the quantity of electricity in coulombs needed to reduce 1 mole of chromate, dichromate? Answer is very easy if you understand the number of electrons transferred. How many electrons for 1 mole? How many electrons are getting transferred? 6 electrons. It means it is 6 moles of electrons for 1 mole of dichromate. It can be potassium dichromate, for example. So if you can understand this, you can get the answer. So 6 moles of electrons will correspond to 6 into 96,487 coulombs. So we can get total charge by simply multiplying it by 6. So what is the quantity of electricity in coulombs needed to reduce 1 mole? This is the answer. Vanna Ashi, yes, correct. Now batteries. So any battery as a source of electrical energy is a galvanic cell where the chemical energy of the redox reaction is converted into electrical energy. This is something you know. There are mainly two types of batteries, primary batteries, secondary batteries. However, I have explained it in detail, but primary batteries are those ones which are used up and cannot be reused, cannot be recharged. These can be recharged and then reused. Secondary batteries. That's the only difference. Okay. So primary batteries, dry cell and mercury cell means these cannot be charged. Dry cell, mercury cell, once used, you have to throw. Shashwat, yes, that can be used as Q equals to Ne. But in this chapter, because you know Ne is actually 1 Faraday. If N is 1 mole, then Ne is 1 Faraday. So you can save time. Instead of multiplying these two, you can just write 96,487. Otherwise, you will multiply and then you will get 96,487. Yeah. Shashwat, is that clear? What I am saying? Yes. So two cells as primary batteries. Once used, you can't recharge these, dry cell and mercury cell. First one is dry cell. The most familiar example of this type dry cell is Leclanché cell. Basically, that is the name of the scientist, which is used commonly in our transistors, clocks, etc., remotes. So you have AA size, AAA size. Okay, those are actually dry cells. So when we talk about Leclanché cell, the cell consists of zinc container. The container is made of zinc and also acts as anode. These are the points I have highlighted so that you can memorize these points. These are answers to questions. And cathode is carbon graphite rod. Container itself acts as anode. So you can just visualize you have a pencil cell. Whenever next time you have pencil cell, triple A size, double A size in your hand, just think about it that the container, outer container is actually anode surrounded by powdered manganese dioxide and carbon. So manganese dioxide and carbon is here, which is also known as carbon black. And cathode is just a carbon rod. The space between the electrodes is filled with moist paste of ammonium chloride and zinc chloride. It is filled with ammonium chloride and zinc chloride. All these points you have to memorize, write it and memorize it. In this section, there is nothing which should be explained much. This is more about you need to memorize, you need to remember. The electrode reactions are complex, but they can be written approximately as follows. Now remember, these are not exactly what reactions happen. These are just few metals and compounds only which we are considering. There are other reactions also which happen, which take place. We are not going into those details. Those are not in syllabus. So at anode, oxidation will take place. Zinc will get oxidized to zinc ion. At cathode is carbon rod. Here, manganese dioxide will react with ammonium chloride. This one, ammonium chloride. and will get converted to magnesium oxide and ammonia. Now, one very important question appears, which I will be talking about later. That if ammonia gas is evolved here, why the battery doesn't get busted? Due to pressure of ammonia, it should burst, but it does not happen. There is answer for that I will be talking about later. Now, why I am calling these reactions approximate? These reactions are approximate because if you see, we are not considering all the compounds which are there in the reaction. Yes, everything is not being considered here. For example, carbon is not being considered, and also intermediate reactions are not being considered. In the reaction at cathode, manganese is reduced from +4 oxidation state to +3 oxidation state. Here it is +4, here it is +3 oxidation state. Reduction. At anode, from 0 to +2, increased oxidation. Ammonia produced in the reaction forms a complex with zinc ion. And that is the answer you will write if you get the question, that ammonia produced does not lead to bursting of the cell. The reason is this ammonia actually reacts with the zinc ion and forms a complex. The cell has a potential of nearly 1.5 volts. So whatever cells you have, AA size, AAA size, these have potential as 1.5 volts. Now write in the chat box, what is the potential EMF of Daniel cell? The EMF of, okay, good, Shashwat, yes. I think in the first class we have discussed about it when we talked about the galvanic cell, Daniel cell. For Daniel cell, the potential is 1.1 volt, approximately 1.1 volt. For Leclanche cell, it is 1.5 volts. Reactions are important. You don't need to write complex reactions. These reactions are sufficient. Write down, memorize. Also memorize the formula of complex. This formula of complex might appear like Cl2 here. Okay, so if Cl2 is not written, then you will get 2 plus charge here. If 2 plus charge not there, then Cl2 will be written here. Next, mercury cell. Primary batteries we are talking about. Mercury cell is another primary battery which cannot be recharged. Mercury cell suitable for low current devices like hearing aids, watches, wrist watches, consists of zinc mercury amalgam. Memorize these things, zinc mercury amalgam. As anode and a paste of mercuric oxide and carbon as the cathode. The electrolyte is a paste of potassium hydroxide and zinc oxide. The electrode reactions are at anode from 0 to +2 oxidation state, oxidation, zinc mercury amalgam is written like this. It is also written like dash. It is also written like this. So it is zinc amalgam, also known as zinc amalgam only, because when we talk about amalgam, amalgam logically is only combination with mercury. This word now is being used in English just to say any mixture of anything. But amalgam, if we consider only the original meaning, is the combination of any metal with mercury. That is called amalgam. Even if you just say zinc amalgam, it means zinc and mercury. Reaction, anode reaction, memorize it. Then cathode. At cathode, mercury oxide or mercuric oxide is converted to mercury. Reduction. Plus 2 oxidation state to 0 oxidation state. Reduction at cathode. Write down the reaction. In this section, mostly those students face problem who don't pay attention to reactions. That is the primary requirement to understand and memorize the reaction. This is how a cross-sectional view of mercury cell looks like. The cap here, anode cap, is this metallic disc. The cathode is actually attached to the can. Cathode is actually attached to the can, outer covering. So the outer covering here is cathode. This lower disc is anode. This disc is anode. These two, anode and cathode, are separated by insulator. So here we have insulator. This one is insulator. Which is written here as gasket. So this gasket actually provides separation and insulation between anode and cathode. So there is a separator also which separates the anode and cathode inside. There is a gasket also which separates anode and cathode outside. The metallic parts of anode and cathode are separated by gasket. Internal anode and cathode are separated by separator. The overall reaction, so if you combine these two reactions, you get the overall reaction. H2O, H2O, and these will get cancelled. 2OH, 2OH, 2 electrons, H2O will get cancelled. Overall reaction is this one. This mercury cell has a potential of 1.35 volt. All potentials you need to memorize. Daniel cell 1.1, dry cell 1.5, mercury cell 1.35, and remains constant during its life as the overall reaction does not involve any ion in solution whose concentration can change during its lifetime. Very important answer to a question. You will get a question that which type of dry cell has constant voltage and why? So there are two types we are talking about, primary cells. So there are two types of primary cells we are talking about, dry cell and mercury cell. Dry cell does not have constant voltage throughout its lifespan because when the reaction happens, the ions are involved there. When ions are involved, the concentration of ions gets decreased. But here, the concentration does not decrease because everything is solid. Solid, 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 solid. Liquid here. Pure liquids and pure solids do not have the change in concentration. They do not decide the concentration. So that's why. Very good question appears from here. Secondary batteries means these can be recharged. They get exhausted, can be recharged and used again. Two types we will be talking about: lead storage batteries and nickel cadmium cells. Nickel cadmium cells are again of AA size and AAA size. So pencil cells we normally get, or torch cells, chargeable also. So chargeable ones are nickel cadmium cells. The use and throw type are Leclanche cell or dry cell. Lead storage batteries are these batteries which you normally use in your cars. In your car, the battery is lead storage battery, or in inverters, etc. Lead storage battery consists of a lead anode, anode is lead anode, and a grid of lead packed with lead dioxide as cathode. I'll show you the diagram. And then you need to remember this: a 38% solution of sulfuric acid is used as an electrolyte. In lead storage batteries, the electrolyte is 38% sulfuric acid. Okay. Cathode is lead packed with lead dioxide, PbO2. Anode is just lead. The cell reactions: at anode, you have lead. It reacts with sulfate ions of H2SO4, produces lead sulfate. Oxidation state of lead from 0 to +2. Oxidation. Next, cathode. Cathode is lead dioxide, again with sulfuric acid. Gains 2 electrons released by anode and produces again lead sulfate. These two reactions first you need to memorize. And remember, the type of battery we are talking about is rechargeable battery. Means the reactions can be reversed in a way. That is, the overall cell reaction will be lead plus PbO2 plus 2H2SO4. This is 2H2SO4. And it will give you 2PbSO4 and 2H2O. 2PbSO4 you can write like this. Anode reaction, cathode reaction, overall reaction in all cells important. Write and memorize. Write 3-4 times. Don't hesitate to write now. If you want to reduce your tension during the examination, write these reactions today 3-4 times. On charging the battery, now I'm talking about when we are doing the reverse. On charging the battery, the reaction is reversed and PbSO4 on anode and cathode is converted back into lead and lead dioxide. Reverse reactions will take place. Reverse of these reactions will take place. Okay. Normally, you will be asked this reaction and reverse of this reaction, but you need to remember both: anode, cathode, and overall reaction. And also, if it is asked, write the reverse reaction. For charging the reactions, all these reactions will be reversed. This is how a lead storage battery looks like. Okay. Anode is just lead, made of lead. Cathode is lead filled with lead dioxide. You need to remember these things. Electrolyte is 38% sulfuric acid. Positive plates, lead grids filled with PbO2. Negative plates, lead grids filled with spongy lead. Anode is this part, blue part. Okay. And you see the negative plate is blue plate, which is connected to anode. And you know that anode is negatively charged. When we discussed the Daniel cell, galvanic cell, we talked about anode is negatively charged because the current flows in the outer circuit, current flows from the cathode to anode. And current always flows from positive to negative terminal in outer circuit. And positive plates are cathode. Okay. These ones, cathode here. So just try to remember these things. Negative plates obviously will have only lead. So these are made of lead and are filled with spongy lead. Spongy lead actually makes the reaction faster. Positive will have lead grids, solid lead grids filled with lead dioxide. Reactions, these are the reactions you have to remember. Next one is nickel cadmium. Nickel cadmium is again secondary type of batteries, means these can be recharged and reused. This cell has longer life than lead storage cells, but more expensive to manufacture. Overall reaction during discharge means when it is being used. During usage. Cadmium, nickel hydroxide, they react and they produce cadmium oxide with a nickel hydroxide, but here you see nickel is in +2 oxidation state, here nickel is in +3 oxidation state, and water. Cadmium gets oxidized, 0 oxidation state to +2 oxidation state. Oxidation at anode. Here +3 oxidation nickel to +2 oxidation. OH3 means +3 for nickel. Here OH2 means +2 for nickel. So this one is reduction at cathode. This is just indicative diagram of a nickel cadmium cell. Indicative diagram. Normally it won't be asked. You just need to know a few things, and that's why this diagram is here. That these are plates, there are plates, positive plate and negative plates. These are rolled into a cylindrical form and these are separated by some insulator. There can be multiple positive plates, multiple negative plates, one over the other, separated by separators and rolled into a cylindrical form. Okay. Positive plates are connected to the cathode. Negative plates are connected to anode. This separator layer is made of sodium or potassium hydroxide. This is NaOH or KOH solid form, just moist. It is solid but moist. Separator. Now my question is, mm, yes, here my question is, positive plate and negative plate, when we say here, positive plate which out of nickel and cadmium, which will be at positive plate and which will be at negative plate. Tell me in the chat box. These type of questions will appear. In this cell, nickel cadmium cell, which one out of nickel and cadmium is cathode, which one is anode? Okay, good. Yes. Ashies, Mehak, yes. Shashwat, yes. If you see here, cadmium is getting oxidized, means it is anode. Nickel is cathode. Cadmium will be at anode. Negative plate is anode. Positive plate cathode. Nickel will be there. Reduction will take place. Nickel plus 3 will get reduced to nickel plus 2. So here nickel 3 plus 2, nickel 2 plus reduction, and at anode CD 2 CD 2 plus oxidation. Next topic, fuel cell. Within batteries, fuel cell. Yastika, what I was explaining that at cathode reduction will take place, at anode oxidation will take place. Hence, as per the overall reaction of nickel cadmium cell, cadmium will be at anode and nickel will be at cathode. Fuel cells. These are a special type of cells, and when we say fuel cells, means we can provide the reagents needed to run the reaction. Now, what is the problem with other cells? That once the compounds are exhausted, for example, in dry cell or in mercury cell, once the chemicals are exhausted, it is discharged. It cannot function again. But fuel cells are those cells in which we can continuously provide the chemicals, that is reagents, required to run the reaction. So we keep on providing the reactants and the reaction continues, keeps on running. So they can keep on running for years if we keep on providing the required chemicals. So it is possible to make such cells in which reactants are fed continuously. to the electrodes and products are removed continuously from the electrolytic compartment. Reactants are being provided, products are being removed continuously, and cell keeps on running. These are called fuel cells. Galvanic cells that are designed to convert the energy of combustion of fuels like hydrogen, methane, methanol, etc., directly into electrical energy are called fuel cells. Remember, the thumb rule applies that you have to keep on feeding the reactants and you need to remove the products. One of the most successful fuel cells uses the reaction of hydrogen with oxygen to form water. The cell was used for providing electrical power in Apollo space program. To generate the power, this type of cell was actually used in Apollo space program. And the water vapor produced due to the reactions in the cell, these were condensed. These were pure water vapors. So those were actually condensed and used as drinking water for astronauts. So the water vapors produced during the reaction were condensed and added to the drinking water supply for the astronauts. This has a very simple diagram of hydrogen fuel cell. Very simple, very simplified version of hydrogen fuel cell. And because it is simple, it is asked to draw this diagram. Hydrogen and oxygen are the reactants, and H2O is the product. Cathode, as usual, positively charged, anode, negatively charged. Towards cathode, oxygen is there. You need to remember these things. Don't just interchange these. So, what anode, you have hydrogen. These are porous anodes and cathodes. Otherwise, hydrogen will not be able to react. Porous anode, porous cathode. They have pores. In the cell, hydrogen and oxygen are bubbled through porous carbon electrodes into concentrated aqueous sodium hydroxide solution. From anode side, hydrogen; from cathode side, oxygen. Porous carbon electrodes. Catalysts like finely divided platinum or palladium metal are incorporated into the electrodes for increasing the rate of electrode reactions. Within the porous carbon anode and porous carbon cathode, finely divided platinum or palladium metals as catalysts are used. Remember these points. The electrode reactions are at cathode, because from cathode side, oxygen. Cathode reacts with water and produces hydroxyl ions. At anode, hydrogen is there. It reacts with these hydroxyl ions and you get double the amount of water. You use 2H2O, you get 4H2. Now, these reactions are not as written in NCRT book. So write down these reactions and memorize. Quite a few things what I am talking about, a few steps might not be there in NCRT. Reactions of fuel cell, hydrogen fuel cell. And when you combine these two, you get the overall reaction. Overall reaction is very simple. 2H2 plus O2 gives you 2H2O. So to understand, just a summary, porous anode, porous cathode with finely divided platinum or palladium as catalysts. At anode, hydrogen; at cathode, oxygen. Concentrated sodium hydroxide solution here, in which reaction takes place, and water vapors are evolved. The cell runs continuously as long as the reactants are supplied. Means we keep on providing hydrogen and oxygen, we keep on collecting the water vapors, the cell will keep on running. Because if you see the reactions, in these reactions, we are not using anything like NaOH, concentrated NaOH solution, or platinum or palladium. Those are just platinum, palladium as catalyst, and concentrated NaOH solution, just the medium, basic medium. Another important thing about fuel cell, its efficiency is 70%, as compared to thermal plants whose efficiency is only 40%. Means the energy on the left hand side and you get the energy on the right hand side. In case of fuel cell, if here energy is 100%, you get 70% of it, 30% is lost, used within the reaction or in other, you know, processes. 70% you get in case of fuel cell, only 40% in thermal plants. Because in thermal plants, there are a lot of processes where you waste the energy. In fuel cell, hydrogen fuel cell, it is just the reaction being done there. You just need to provide hydrogen and oxygen. Moreover, fuel cells are pollution free. In thermal plants, you have to produce heat, for that pollution is there. Here, there is no such pollution. Next and last topic of this chapter, corrosion. And this is something you already know. The only thing about reaction and where oxidation is taking place, what reduction is taking place, that is important. Otherwise, you already know what is corrosion. Corrosion slowly coats the surfaces of metallic objects with oxides or other salts of the metal. For example, in case of iron, it is rust, Fe2O3. And in case of copper, it is the salts basically, not oxide. Copper carbonate and copper hydroxide, green color from that. So examples, rusting of iron, tarnishing of silver, development of green coating on copper and bronze. These are the examples of corrosion. In case of iron, this has been given a specific name, rusting. So corrosion of iron is known as rusting. We don't use this term for other. For silver, we use the term tarnishing. General term is corrosion. All are corrosions. Iron is called rusting. In case silver, tarnishing. This is something what you can understand with the reactions. And if you can understand just the reactions, that is sufficient. oxidation and reduction we need to understand. So iron gets oxidized to Fe2O3. So Fe2 plus is actually, sorry, FeO. So Fe2 plus is actually FeO here in this case. Okay. Overall reaction, yes, we will be talking about there will be Fe2O3. So what happens? Here you have iron. And here you have oxygen, atmospheric oxygen, atmospheric oxygen. Okay. So different types of reactions are taking place here. There is moisture within the air. Rusting of iron we are talking about here. The example is talking about rusting of iron. First, you need to understand rusting of iron takes place only if both oxygen and moisture are present. Rusting of iron will not take place if moisture is not there, only oxygen is there. Rusting of iron will not take place if only moisture is there, oxygen is not there. Both have to be present. Okay. So what happens? The iron, due to atmospheric oxygen, gets oxidized and then further oxidized to Fe2O3. So first it is getting oxidized to Fe2 plus, and then from Fe2 plus to Fe3 plus. Fe2 plus is FeO, Fe3 plus is Fe2O3. So in these reactions, when I am writing Fe2 plus, it means I am talking about FeO, ferrous oxide. Fe3 plus means ferric oxide. And ferrous oxide is not rust. Ferric oxide is rust. So normally you won't have ferrous oxide because the moment you get ferrous oxide, it gets oxidized to ferric oxide. So this one is just intermediate. It will get oxidized to ferric oxide. So what happens? During this conversion, it loses 2 electrons. Okay. When two such reactions happen. One, you get total 4 electrons. These 4 electrons are used for reduction. So this is a redox reaction basically. In this case, oxidation and reduction both are taking place. So corrosion is a redox reaction. So these 4 electrons are used by atmospheric oxygen and moisture. Okay. So this 4H plus and H2O are actually interrelated here. The moisture actually provides you the hydrogen ion, although it is written like this because it is converted into water, but it is there in the moisture. In the moisture, it is there. It gets combined with oxygen and the 4 electrons are used from here, and you again get liquid water. Reactions you need to memorize. Reactions are slightly complex, although here the reactions are not actual one. These are simplified versions of actual reactions. Okay, cannot be simplified further. So simplified versions are written here. You just need to memorize these. And then the atmospheric oxidation takes place. Atmospheric oxidation means this Fe2 plus gets converted to Fe3 plus. So this is that reaction which takes place. So in this case, two oxidations are taking place, as I am saying again and again. First oxidation converts to FeO. Then again FeO gets oxidized to Fe2O3. So that's why you have two oxidation reactions, this one and this one. First oxidation from Fe2, Fe2 plus. Second atmospheric oxidation written there as Fe2 plus to Fe3 plus. As I said, for other reactions also, write these reactions 3, 4 times. You have to memorize. Now, how you understand these three reactions? To understand these three reactions, first understand the oxidation only. Means first to here and then from here to Fe3 plus. It means you have to you have considered this reaction also. Now, if you observe this reaction, which is actually happening here, it releases 4 hydrogen ions, 4 protons actually. These are used here along with the electrons here, 4 electrons, 2 reactions along with this one. So these provide here this from here, and this reacts with atmospheric oxygen again and gets reduced to water. Now you might wonder that when water is being produced, why I am saying that moisture is necessary, and without moisture the rusting cannot take place. For that, just consider the point again. I said first consider the oxidation only. So when you consider oxidation only, this is the step 1 and step 2 here. Within that you need moisture. This is actually from moisture. Although you get it back into the atmosphere, but first it is required. First it is required for H plus, and then it is produced again, but first it is required. So Hina, I'm muting you. In corrosion, a metal is oxidized by loss of electrons to oxygen and formation of oxides. Formation of oxides means here FeO or Fe2O3. Loss of electrons. Electron loss. Oxide form. Corrosion of iron, commonly known as rusting, occurs in presence of water and air, or moisture or air. At a particular spot of an object made of iron, oxidation takes place and that spot behaves as anode, and we can write the reaction as iron gets oxidized to iron oxide here, and then again this Fe2 plus gets converted to Fe3. So electrons released at anodic spot move through the metal and go to another spot on the metal and reduce oxygen in the presence of hydrogen ion, which is believed to be available from H2CO3 formed due to dissolution of carbon dioxide from air in water. Believed to be. Okay. These can appear as per this reaction as well. This is the reaction I have shown here. Okay. 4H plus. But it is also considered that these protons might appear due to the carbonic acid present in the water, in the air. Air contains carbon dioxide, and when carbon dioxide gets mixed with water, moisture, it produces carbonic acid. So that's another possibility. Okay, another possibility, I'm saying. Carbon dioxide present in air when reacts with water produces H2CO3, carbonic acid. So it is believed that this carbonic acid gets ionized in proton and bicarbonate ion. So these might be obtained from there as well. Hydrogen ion in water may also be available due to dissolution of other acidic oxides from atmosphere, not only carbonic acid. Other oxides, acidic oxides in the atmosphere can also provide H plus. So 3 points, remember, I am talking about. You will write the reaction as written here, that this H plus is obtained when Fe2 plus is oxidized to Fe3 plus. In reaction, you will say that these are made available during the atmospheric oxidation of ferrous to ferric. But these hydrogen ions here can be from other sources as well. So it is believed that these can appear from carbonic acid also, these can appear from other acids also in the atmosphere. This spot behaves as cathode, where reduction is taking place, that behaves as cathode. So if I show you the diagram, in the diagram, here oxidation is taking place. Here oxidation is taking place. So this whole is actually oxidation region, and this whole is reduction region. So here oxidation is taking place. If a point is asked, then you will show this point, oxidation, and here reduction is taking place. So at cathode, reduction takes place. The overall reaction you will write like this. Iron gets oxidized. Oxygen will get reduced. Oxidized from 0 to +2 in this case, and reduced from 0 to -2. The ferrous ions are further oxidized by atmospheric oxygen, which is Fe2O3, and there are some water of crystallization also. This X can be 2, this X can be 3. Some water of crystallization attached to that. This is known as rust. Prevention of corrosion, how we can prevent corrosion. One of the simplest methods of preventing corrosion is to prevent the surface of the metallic objects to come in contact with atmosphere. Means break the contact with atmospheric oxygen and moisture. So one is paint. Paint the surface by some chemicals, for example, bisphenol. Another simple method is to cover the surface by other metals. Instead of paint, cover it with metal. For example, tin and zinc that are inert or react to save the object. So the metal covering can be inert and metal covering can be the reactive also. So instead of the iron metal, so suppose I have an iron object and I get a metal surface over it, another metallic surface over it. So there are two possibilities. Either this metallic surface is non-reactive, inert. So this is one way. Or this metallic surface reacts but saves iron. Reacts but saves iron. So in this case, it is known as sacrificial, means it sacrifices itself and saves iron. So An electrochemical method is to provide a sacrificial electrode of anode metal like magnesium, zinc, etc., which corrode itself but saves the object. For that, we use electrochemical method, means electroplating. Now the question. Suggest two materials other than hydrogen that can be used as fuels in fuel cells. The answer is methane and methanol. If you remember, when I talked about fuel cell, here I talked about hydrogen, methane, methanol, etc. So three, you need to remember hydrogen, methane, methanol, which can be used in fuel cell.